Okay, welcome back. Now I'm going to continue with the trackers. I hope you enjoyed the first part, by the way. But to tell the truth, the next part, the next algorithm will be a little bit more uh, complicated. I hope I can explain them very well. Now the next one is called CCOT, the continuous convolutional operators for tracking. Before starting, let me tell that method is also very powerful, and it won the 2016 Watt Challenge. And it gave very good results in the next year as well. It's a very strong, interesting algorithm. Now let's start. Uh, in the year of 2016, now the convolutional neural networks were everywhere. Therefore, they were creating very valuable representations with their multi-resolution architectures. Therefore, in a deep network, in the first layers, there is some very low-level information which could be used very well for trackers. In the higher, deeper resolutions, you will have a semantic information which can be also utilized by the trackers, especially when there is some appearance changes. But how to combine these things, especially realizing that typically these structures are getting smaller and smaller due to the pooling stages. Therefore, that algorithm, in fact, is just an approach for combining the different information in the layers of convolutional neural networks. The thing is, we are trying to combine discrete time. The DT stands for discrete time, by the way. This is the discrete time. We are having some learned, trained information of using CNNs, and they have different resolutions. Especially semantics are lower resolution, or low-level information is the higher resolution. And we are trying to combine them in continuous time. CT stands for continuous time. Well, using computers, we will do something in the continuous time domain. That's a really interesting idea. Now, let's see how we are doing it. First of all, let's assume this is our typical feature D, whose size is ND. And we have this discrete time signal, a feature. I am interpolating just in this Nyquist sampling theorem by an interpolation filter here, okay? And this kernel, this is a kernel, a continuous time kernel in terms of t. Now it takes xdn, and it basically, for every sample that we have here, we put a corresponding kernel, interpolation kernel, and at the end we add them up. And let's see how does it look like. Therefore, if this is your xd of n, the discrete time signal here, these are our kernel. Here we are not having a sync type, but rather than we have a spline, bicubic spline type kernel here. Therefore, for every such data, we are shifting it and adding that, and we obtain such a result at the end. Now, one interesting thing to note here is I am assuming that this signal is periodic with ND. Hence, this is also giving us some data, and the shifted and summed version, it also gives you something periodic. Okay, therefore we repeat it itself, and we obtain something periodic here in the continuous time. Okay, that's an important thing to realize, because at that point we are saying that I am just having something which is periodic, which results that this thing becomes periodic as well. Okay, and the resulting continuous time signal is periodic. Now, we did interpolation using some kernels, continuous time kernels, and in the meantime, the resulting thing we did, we also tried to make it periodic so that we can use continuous time Fourier series to represent it using some discrete values, some coefficients. Now, this is the step where we make the combination of resolutions. Therefore, with different kernels, different resolutions are added, and please note we can have, for a given D resolution, we obtain this result. Now, for the same given D resolution, this result, this continuous result, is convolved with a continuous time filter. Now, this time, we are also trying to obtain a continuous time filter, okay? Now, these two continuous time signals are convolved for every resolution, and we obtain a continuous domain response. This is our continuous domain response for this input with this filter, and that is this result. Now please look at here. We are having everything is continuous here, okay? Now, and from these continuous reconstructions of XD and the continuous outputs, we obtain such a result. Okay, this is S of F. Okay, we are having this. Now our X, the X is nothing but our discrete features from a CNN, for example. Now, please note, I obtain XD as a combination of these things, but in the continuous time. Therefore, this XD, JD is something continuous here. It's a continuous convolution here. FT is a continuous filter like this one. And we are convolving, and for every D, we adding that. And please note, this is a convolution. But one thing to note, we chose, or we select, or we enforce our filter to be also periodic. Therefore, this is periodic with T, that is periodic with T. In fact, this convolution we are talking about is a periodic convolution. I hope you are you are understanding why am I reaching to? Because if we are talking about periodic convolution, then multiplication in terms of continuous time Fourier series coefficients will help us. Now, again, this is continuous, this is continuous, this is our aim, and this is the response, and that response is also continuous. Starting from X, everything is discrete. I am reaching to something continuous, and that peak will tell me where will be the location of this next object moving, okay? Now, the resulting cost function in continuous, again, you can be minimized to determine the continuous time filters, FT, from the training data. Now, as before, this is our alpha J, which is the impact factor. Our IIR filter is basically handling this, which is giving more emphasis to the near time data, less emphasis to the far away data, okay? This is our nothing but this thing subtracted from a desired, again, continuous time response. Now, plus the next term is from SRDC, again, WMAP, a special regularization term, which will help me to enlarge this green bounding box to a larger size, but still the filter will be focused inside. Therefore, that will help me to find a larger search space, a larger support, but in the meantime, the filter is just focusing on the small green box typically. Therefore, but everything here is continuous. Every result here is continuous. Now, how to solve this continuous problem in discrete world? Okay, now this is the cost function that I minimized. These are the things. Once again, let's look. Data is discrete. This is our Gaussian just in the frequency domain, continuous again, a continuous Gaussian converted into a continuous form. This is our filter, continuous. This is our special regularization map is continuous. F is unknown here. And here we have again, periodic convolution. And that result will give us, for every such D, okay, we will have a final result, and we will just combine them. Because everything is continuous right now, every result here is between 0 to T, continuous T, and we are just adding all these things. The interpolator is appropriately converting everything periodic between 0 to T in continuous. Therefore, after this interpolation, just adding them is trivial. But still, how to do all these things in using a digital computer, okay? Now, we have to go to the, again, the Fourier domain. just for computational purposes, but this time it will be more tricky. Now, please note that was the point where we have stopped. Interpolating kernel, a standard cubic spline kernel, which is also periodic with T, okay? And we have this XT weights. If you take, this is also periodic, we made it periodic because due to this we have some periodicity here, okay? Now, having this periodic, we can take the continuous time Fourier series of the right hand side, okay? And obviously the left hand side as well. Therefore, now everything here, this is a continuous time Fourier series representation because it's a continuous time periodic waveform, which is in terms of weights, linear, this is linear weights, times, hey, this is shifted. This Fourier series also have the same shift property. It will be e to the minus j 2 pi n d kn, okay? But it will be 2 pi over t, then t over nd makes this 2 pi over nd. You can just work it by yourself, okay? And finally, nothing but the Fourier series of BD. Okay, this is the cap, it stands for the Fourier series. Now, this is independent of n, therefore it goes out here. This is with respect to k. And that thing will be inside xt of n e to the minus j, this one. Please note that this is, in other words, this is nothing but dft of xt of n. What I'm doing is this, I take the dft of xt of n, and I obtain this result, okay? That result, and the continuous time Fourier series coefficients of this thing, which is my interpolated response, is nothing but our input signals dft at nd point, and nothing but this multiplication of this thing with the continuous time Fourier series coefficients. Now here comes the little trick. Let's write the cost function in the frequency domain instead of SF. Please note again, since I am doing a periodic convolution here, therefore I have to have nothing but multiplication, okay? Therefore this is having some periodic convolution inside. Therefore I will have these two terms, BDXT, okay, these are here, we are having here, they are in the frequency domain. Now I just multiply it, the Fourier series coefficients of this periodic filter here as well. These are all in Fourier series, okay, coefficients. And you do this and you add them for every different resolution of the CNN. And don't forget, you are subtracting with the desired response. This is again, this is periodic. This is also made periodic. You obtain Fourier series coefficients. Now everything is beautiful here. Everything is again in the frequency domain in terms of Fourier series coefficients. And our final term is still here, the filter that we are trying to find, okay? And that has to be again convolved with something this, which is also periodic. Therefore, multiplication of these things will be again in the frequency domain. It will be a convolution, but periodic convolution of these things as well. Okay. Now, and this is the corresponding Gaussian term, which is basically this term here, the Fourier series coefficients of it. Now, we are trying to calculate periodic continuous time convolution, and we obtain the corresponding continuous time Fourier series, and we convert it to our all formulation into continuous time Fourier series coefficients. But at this point, now the magic disappears. Please note those coefficients can go to infinity. The continuous time Fourier series coefficients can go to infinity. Here comes a little trick. The authors basically truncate them into some ND samples, okay? Because otherwise you cannot continue with the computers. You have to fit everything into some finite vectors or arrays, okay? And they just make a truncation, and they continue from this point on in the Fourier domain, but using truncated Fourier series coefficients. The rest will be a little bit math and optimization. We will define some auxiliary matrices A and W, W is nothing but the previous trick. This thing is, this convolution can be written like a matrix form, and that matrix is this matrix, which is here, okay? This is the vectorized of this. You convert it into this vector convolution becomes a matrix multiplication with the vector. This A is nothing but these terms here. X and BD terms are in the diagonals of this, okay? And if you take the derivative with respect to F vector, you will obtain this result. This gamma is the diagonal which is showing these alpha weights here. This is the diagonal matrix with the weights are selected like that, which is giving less emphasis as before, as I have said before, to the previous old samples. Now, this A matrix is nothing but, as I've said, in terms of these Fourier series coefficients, and here is your result, okay? That result is basically, this time, an optimization technique, although you can maybe obtain a result by taking a pseudo-inverse kind of thing, but for online tracking, for solving it in a faster manner, we basically use an optimization technique called conjugate gradient, and iteratively we solve for this result. Okay. Therefore, that algorithm is one of the most powerful algorithms in tracking community. It's working about a few frames per second, although these have these iterations. It's no more a beautiful closed form expression for the DFT and all the previous things in DSST or MOSSE, but here we are having some iterations, but those conjugate gradient iterations are typically performed only 5 or 6 iterations as far as I know. Therefore, this is relatively a short number of iterations that we are trying to achieve. CCOT is again a very powerful algorithm, and it solves merging the different resolutions in an efficient way. Just a little advertisement here. In 2017, myself and my PhD student Erhan, we just take the CCOT and we take this cost function and we basically use this cost function as a as a back propagation in the back propagation step of a CNN, and we just train our system. We train our weights using this cost function and appropriately changing our CNNs, not a pre-trained CNN for a different application. We basically used this cost function to train our CNN, and that result basically beat the CCOT in 2017, and we basically won the contest. Okay, but years go by, then new algorithms basically appeared. One of them is called efficient convolution operators for tracking, called ECHO in short. Okay, these deep networks has led a radical increase in the number of appearance model features, and we have lots of features. If you combine those features, they were improving the result a lot. But in the meantime, it's becoming far away from the real-time performance. This echo tracker is basically an approach to solve this complexity problem. The baseline is CCOT. The learning step is the bottleneck. Okay, during the optimization-based DCF trackers. Okay, you have to have some conjugate gradient approach to obtain your result at the end. And echo is basically trying to obtain those filters in a faster way. The idea is this: these are nothing but our filters that is obtained through CCOT. Okay, all these things are the filters. Look at these filters, and most of them have negligible energy. Only a few of them has some sufficient energy to make a discrimination for target localization. Most of these things are in a way useless, but for every such D, this is 1 to capital T here, capital D here, we are trying to find the filter. All of them, we have one filter for each. This is somewhat useless. Therefore, the authors, again, the same authors from Linköping University, they try to have a smaller set of basis filters like these filters here with limited number. These filters, we are writing every individual filter in terms of these filters. Okay? Therefore, what we are trying to aim is this. Instead of going and calculating all these filters, let's have a smaller filter size like this one, and obviously some P matrix, which is every filter with which combination we have to add them to obtain one of these things. P matrix stores this information. Therefore, we are trying to obtain limited number of filters, and the P matrix giving the which combination scalars we have to use to combine them, PDC scalars. We have to learn these two things together instead of learning these redundant set of filters. Now, if you look at the previous formulation once again, I'm talking about F, which is nothing but these filter set, multiplying P, every individual DC is giving at the end, after this matrix multiplication, you obtain these individual ones, okay? And those individual ones, okay, will give you just the previous formulation that we have. But we do a little trick here. Instead of just multiplying this one with F, I just multiply the transpose of this, because the transpose will give the same result. And this, I just put this transpose to here, and I'm just first take the response, the continuous response of the CCOT, we multiply with this PT first, and then only find those F filters from here. Therefore, I have two things to estimate. This F filter, these guys, instead of the whole thing, and also this PTs, these coefficients, which we'll basically using to obtain these results. Now, again, we will go to the continuous domain, okay? We are here in the continuous domain. Z is our input. F is the unknown filter. Z is obtained like this JX here, okay? P is our nothing but the unknown weights, which are combining the bases appropriately. Y is our Gaussian, which is the desired response. Again, from SRDC and CCOT, this is this special regularization term. And final term here, it puts the last term for regularization saying that the P coefficients, their energy should be low. Okay, it should not be too much. There shouldn't be too much P values. We are trying to obtain as small as possible P values, just like in the sparse coding concept. We are trying to use small number of basis vectors to achieve this goal. ZT, as I have said before, is nothing but our previous, the individual layers just multiply with the Fourier series coefficients of the interpolating bicubic spline. Okay, now again we were here. This time it's much difficult. This time the cost is nonlinear. Why nonlinear? P unknown and F unknown, they are multiplied. Therefore, right now we are having a problem of nonlinearity. It's getting more difficult. Now let's do a little trick here. Let's open this nonlinear function around the current estimates of P and F, the current filter and the current weights, plus some delta improvements on top of them. If you have multiplied these things, there are four terms. This F tilde I theta, this is nothing but this sum, okay? Therefore, I just write the sum together. This term and that term will bring pi and delta pi, okay? But right now, I am just, with a small approximation, instead of this fi, I just write it instead of fi delta, I write it fi here, okay? Now, this comes in this way, okay? This is exactly equal to here, and that becomes a Kroner delta product, which is a conversion of a matrix times a vector of this thing here, and the corresponding minimization. Now it's linearized in some way because this is known. This is known to us. This is unknown, delta here. This is known. This is unknown. Yes, this is a linear problem here this time, and I can approach the problem here in this way. Using conjugate gradient as in CCOT. The weight strategy, as I have said before, is again, will be utilized here. Now, until now, what we have obtained is nothing but the solution of our original MOSE formulation, then DSST, then SRDC, then CCOT, and here comes the echo. The echo is right now linearized, nonlinear solution, and it's ready to be solved again, as in just CCOT. Echo algorithm gives one more little extra information or one more novelty that I have to mention. Echo realizes that this inclusion of the past samples using such a weight importance weighting strategy is somewhat insufficient because in typical video sequences, this very same redundant information is in the time sequence, and a new real useful appearance will sometimes get a very small alpha k value because it's maybe about 100 frames behind. Therefore, instead of naively using the time information, maybe we have like this kind of information. Okay, data goes here. There is a guy here, the same guy. Then it opens the hands like that. It continues. Now the alpha k becomes very small here. Okay, we are only having this appearance basically dominating everything. But in the next frame, maybe the guys open the hands once again. Okay, we are opening the hands once again, but this information is lost due to alpha k small. Now, can I use a trick so that those redundant frames are not used, but only this information with some different appearance information available can be used in the training data? In other words, I want to get rid of these frames, those frames. I just want to use this one, and the similar important information during my training strategy so that in the new data, if something from the previous comes, I can still find it very well. Now that's a little trick they are using. Instead of using a large set of frames with redundant information, a generative, probabilistic generative model is utilized. Whose generative model? The generative model of this one and the corresponding positions, okay, X and Y. Until now, we are always, in fact, using such an approach. We were using this approach here. If you assume that I have an impulse, just giving a constant 1 at the correct xk value. In other words, this is one appearance, okay? This is another appearance. And what we are doing is, if this appearance is correct, then we obtain nothing but the corresponding alpha k. Otherwise, we will obtain 0. The trick is, let's write this p of xy as the appearance of the object time delta y minus y0. First of all, y0 is nothing but the position of the object, and still let's use it as an impulse. But the p of x, let's model it using a Gaussian mixture model with L terms. In other words, this is first appearance of the Gaussian mixture. This is the second appearance of the Gaussian mixture. Okay, we have such L terms, and we will only consider the mu L is this guy, the mu 1 is this guy. Therefore, what I'm trying to do is this. Our Gaussian mixture consists of only in terms of non-redundant necessary appearances of the object, and we have L of them with the corresponding weights pi, and we try to obtain such a Gaussian mixture model, and this Gaussian mixture model will help us to minimize the error. Which error? Now we call it expected correlation error. What is this expected correlation error? The same concept, but every term here is multiplied with the corresponding p of xy. I was doing the same thing until now, in fact, using such a impulsive joint PDF. But here, this time a Gaussian PDF, if you have, if you have a, a, a redundant information here, okay, a sample which is coming from something near the mean, you will have a high weight for this one, okay? Still, your probability will be high. If something away from that one, different from that one, the expectation will be small. Therefore, that first term is just replaced with an expected correlation error. The second term still exists here, and that brings us nothing but multiplying our mean vectors. Okay, the difference between the mean vector of this, of every appearance, and you try to find an F filter which is trying to make a good match with one of these mean vectors. In other words, what we are doing is for every different appearance, there is one uh, component in the Gaussian mixture model. This is one mixture model, this is another mixture model, and what you are trying to do is you are trying to obtain a filter which will, once it's convolved with these mu1 and mu-l, which will try to get the result at the correct y0 location, okay? That's our aim, and such an approach, again, will improve the appearance much better with respect to the past results. Now, I will conclude this DCF techniques by a final technique from last year, 2019, called ATOM, accurate tracking by overlap maximization. Okay, that's also a very interesting and elegant technique, but it is slightly different from the the DCF-based, discriminative correlation filter-based techniques, because right now we are focusing more on deep networks. Now, our aim is simply utilizing the main trend in object detection. What is the main trend in object detection literature? Independently, for every frame, people are basically using some pre-trained networks to detect the positions of the objects. Hey, I can use this idea for tracking, but if your object is not in the training set of your pre-trained network, you cannot find it. If your pre-trained network is only finding dogs and cats, if a human comes into the picture, your object detector will not work. ATOM is trying to find the bounding box, but it doesn't try to do it with the limited set of the pre-trained network training data, and it will do it in a more general way. Unlike object detection, the target object, human, does not necessarily belong to the predefined classes like cats and dogs, where your network is already trained. Therefore, you need an approach target specific intersection of over unions. Now, what is this intersection over union? Maybe I forgot to mention this. If we are trying to find an object, if this is your ground truth, okay, this is the human here, and this is your result here, intersection over union, I just realized that I forgot to even define this. This intersection area is A1. The union of these two areas are A2. Obviously, this bounding box ground truth and your estimated result, that should be go to 1, okay? That should be go to 1. This is your ideal scenario. Now, what I'm trying to do is this. I'm gonna predict a bounding box. During training, I'm gonna just minimize the error between the intersection over union between my prediction and the ground truth and the real ground truth, which is equal to 1, okay? Therefore, I'm just trying to make my intersection over union prediction to be as good as possible. I'm repeating once again. I predict something. and this is the ground truth. The real intersection over union is 0.7. Okay, using the ground truth, you exactly obtain this ratio is 0.7. What I'm saying is this: you will predict your intersection over union. You will predict this as 0.6. During training, you will try to minimize this so that your network is predicting your intersection over unions. That's a real good idea. Your network is not only predicting the bounding box, it is also saying that that bounding box is 0.6 quality with respect to an unknown ground truth. During training, we have it. We can enforce, we can train our network to feed this error, but in practice, that's not available to us, okay? Therefore, that's how it goes. This is the test image. This is the reference image. A typical object detector gives you some bounding box estimates. Now, our predictor, this is our predictor. It inputs the features from the current frame, okay? The features from the reference frame. This is your current frame. The bounding box estimates, these estimates from the current frame. The features coming from the current frame are coming from this ResNet network. They come here, the bounding box and the corresponding estimates. It inputs here. Now we have a, during training, offline. This is offline training, the blue offline training here. This is pre-trained network. Okay. Now the ground truth, bounding box, and the corresponding ResNet, it comes to here. Together, after a trick I'm going to explain shortly, they go in input to this predictor. This predictor should be capable of this blue one, 0.722. The purple one is 0.61. The brown one is 0.77. It should be able to make a prediction of this intersection over union. During the training, offline, I'm going to feed this real result. You have a prediction here of the bounding boxes. Please note, these bounding box estimates are the typical object detectors in the literature. Any object detection algorithm will do this bounding box prediction, and what you are doing is simply this IOU predictor giving you a result. Now the output is nothing but the IOU score here. These things are our output. For three different bounding box estimates, we have three different things. Hey, during testing, everything is finished. I'm going to come here. I'm going to look at these prediction results. And among the whole, I'm going to say that 0.77 is the largest. I'm choosing this one. Now, we are done in terms of the training, in terms of the testing. The whole thing here, this thing here, will give you an information about how intersection over union is good quality. The largest one will be our final result. In the meantime, the classifier is also saying that this bounding box estimate has inside the correct current target or not. The confidence will be also available here. Now, the prediction error with respect to the ground truth is minimized during the training, offline training, obviously, and we learn the network parameters. The only missing point here is what is this modulation is doing and how our target specific IOU predictions are obtained. In other words, my user selected target is dog, but the network is trained with the cats. This information should tell me that there is a dog here. And that will be done online. Let's see how could it be achieved. This is the previous network, this network in detail. This is our modulation vector obtained after a few ResNet stages and a few pooling stages I'm going to tell shortly. Now, this pooling stage gives you a modulation vector. This modulation vector has a very important information. This information is about this dog. This is our current target. There is information stored here. Now here comes the next frame. I have some hypotheses. These guys are creating some hypotheses. Okay, these hypotheses are inside this bounding boxes. Okay, the corresponding features are stored here. This, there is multiple maybe hypotheses here. Among these multiple hypotheses, I simply multiply my modulation vector, the information of the current target, visual information, with the hypothesis ones. Maybe this is at the correct location, but there is another one. There is a cat here. This is dog, but there's a cat here. The modulation vector will basically try to suppress the support from here, but it will try to modulate, increase the support of the same information coming from here. This multiplication and pass through a function comes here, and you obtain at the end an intersection over union, which is giving some information about the reference target specific information is available here or not. Okay, therefore this target estimation networks has to be trained offline for a general representation, but then a modulation based network should help me from a single reference target image. From this target image, I have to make a prediction of the intersection over union for specific target, not some predefined classes. The estimated IOU is obtained through some precise ROI pooling, which is a step that being done in the deep network training. Now, the concept is this is the ROI pooling that we are talking about. A typical ROI pooling, you just basically combine all the information inside this box, and this will be propagated to the next layers. You just sum them up, okay? You simply sum them up here. But for in precise ROI pooling, what you are doing is you are just combining every continuous thing inside this arbitrary ROI, precise ROI. This is from this estimated ROI, you have to go to this integer ROI to obtain ROI pooling. But these guys multiply bilinear interpolation multiplication of the weights to obtain these red, to available red thing. And inside this shaded region, we obtain the total weights. Which makes a very precise, accurate information propagation to the next step. And the beautiful part is these weights are basically making your back propagation to pass through here, and the weights could be obtained in a more precise manner in this way. Okay, therefore we used finally some gradient descent procedures to obtain the accurate localization at an online optimization step here. That's an online optimization gradient descent step. What you are saying is, let me change my precise pooling so that the dog will be, the rectangle of the dog is obtained more precisely. This rough estimate is given with the offline training stage, but this precise pooling with the weight updates here, it gives a better precise estimate of the final bounding box so that the ROI pooling and this modulation will improve, get better prediction results. Intersection over union becomes improved. Basically, you are using only 5 gradients iterations for obtaining the final bounding box result. That's all about the atom. In fact, these are all about our techniques that we are using for CDF. Uh, Let me show one little reminder. That was the point where we have stopped. We would like to be robust. ASEF said use a Gaussian to obtain a more robust appearance changes, not only a single peak. I would like to obtain an appearance update. Mosse told us nothing but this numerator and the denominator update using an IIR could be very fast and could be doing very well. The translation is a problem. There is a search space that we have to improve, but the filter is basically has to be emphasized more. SRDZ gave us a good result for this purpose. We need some scale independent results. Scale independency is obtained through DSST. DSST just in a way naively looks for different, but it combined the result in different scales. CCOT is for deep networks combining different features in the continuous time. We were able to do it, and but computation increased, and the echo basically gave us a computation improvement. And finally, ATOM is basically used the improved accuracy by the help of using object detectors at the end. I think this CDF family is one of the best performing visual tracking family, and it's improved until now. Yet, there is still one contender of tracker class called Siamese trackers, which is improving these classes in a way, or at least competing with them. I'm going to just talk about these things shortly. Uh, the Siamese trackers are a group of networks in deep networks where two networks, okay, these are our convolutional layers. We are assuming two networks and they are basically connected to each other. The weights are exactly equal to each other. During training stages, maybe I'm feeding this IT current frame and IT minus one to here, okay? These are our two frames. What I'm doing is I just make these weights exactly equal to each other. I got a representation like IT and IT minus one, the same representation here available, and I combine them or I just compare them to obtain some results. Okay, this is our CNN network based CMEs tracker. Okay, we are having training image, reference image, and the test image. We are trying to find the location of this. They pass through these CNNs, CMEs. They are connected to each other, the same weights, and we obtain a XT here, which is nothing but our result, okay? And we pass it through a correlation filter, and that correlation filter gives us a representation like here, okay? These are the Siamese filters, and these filters, CFNet is basically using a correlation. It gives some results here. And this is a correlation result, which is moving this around the image and find these two spots. And TMRPN is another technique which is following the same ideas behind the state of the object detectors. It does the same thing, just like the modulation here. We are having some weights, and those weights are multiplied and convolved here so that we find this reference to be detected using a uh, uh, correlation-based concept here. Okay, we are using a correlation-based concept here. Where the object detectors are giving you some hypotheses, and you just merge these hypotheses with the available information that you have through a correlation step here, and you look for your best results. And this is called the CMRPN. Both of these results give competitive to CCOT and similar networks. We are not only having we are also making a foreground background classification here in this branch. Okay, the region proposal networks have creating us some different bounding box hypotheses. Okay, and at the end, the template feature coming from here, from the first frame, and uh, we are just combining them. We are on the detection branch. We are just combining those things, and we look for our proposals. And all these proposals, top K proposals, are re-ranked according to their values here. And we just at the end make a decision on among these top K proposals, the one with the largest proposal score will be obtained as the distance. Okay, now let's stop here. I think it's more than 50 minutes again. That concludes our visual tracking part. We will continue afterwards.